All right, today we're going to do section 3.6, which is combining functions, and this is going to be all different ways. So adding, subtracting, multiplication, division, and actually we're not doing those two. So we're only going to talk about composing functions. We're not going to decompose or do the recursive graph section. But the main thing will be combining them arithmetically, which means like addition, multiplication, subtraction, division, and then actually composing them, which is what you typically think of, which is like a function of a function. So like f of g of x, those kind of functions. So all of your functions are pretty much just defined in this way. When we talk about adding, subtracting, multiplying, dividing, the one little bit of notation that sometimes people get confused on is like here. So like fg of x, that means f times g, or f of x times g of x. Addition and subtraction are a lot easier, and then same with division. Now, one thing that's kind of important to bring up is this is pretty simple. This is like adding two numbers. Except now instead of 5 plus 7, you might have 5x plus 7x. Or you might have 5x squared plus 7x squared. Something like that. But the thing to keep in mind is how do these functions, how do their domains change when they're combined? So more specifically, that comes into play with division, because let's say you have just a quick example. So f of x is equal to x squared, and g of x is equal to x squared minus 1. Separately, these two functions are fine. Nothing wrong with the domain. You can plug in any value, and life's good. However, if I do f of g of x, then I end up with x squared divided by x squared minus 1. Now, one other thing to point out, remember, if you're going to cancel something, it has to be factored out from the numerator and the denominator, so please do not say that you can just cancel like this. That's not true. The example I always show is if you had 3/4, that's equal to 3 over 3 plus 1. But that's not equal to, if I cross these out, that's not equal to 1 over 1. So don't cross out just things willy-nilly. But back over to here, now you run into a problem because beforehand, everything was okay. I could plug in any real value and I got out a real value. However, here, I can't plug in positive or negative 1, because if I do, well, as soon as I do, the denominator becomes 0, and that's not allowed. So when you're dividing functions, you have to be aware of what's the original domain, what's the domain of each one, and then what's the domain of the combined one. Now, also another thing is take square roots into account. So you divide a function by a square root. So let's say I threw in over here, what if I threw in h of x is equal to the square root of x? And I did, and I'll write it this way this time, g of x divided by h of x. then I get x squared minus 1 divided by the square root of x. So beforehand, any value was okay for x squared minus 1. You could go from 0 to infinity with 0 being included for square root of x, but now you can't include 0 because if you do, now you're dividing by 0. So you just have to be very cautious with these and exclude any values that will make the denominator equal 0. And another thing here is when we've combined these two functions, the domain has shrunk because square root of x originally is only from 0 to infinity because I can't plug in negative numbers here. And now it's 0 not included to infinity. So just be careful of that. So given that f of negative 2 is 5 and g of negative 2 is 3, what's f minus g of negative 2 and f over g of negative 2? So this is kind of starting with a little bit more of an abstraction part. You don't know the function, you only know the values. So let's start out with that. So f minus g of 2, we know that's the same as f of 2 minus g of 2. And then you can just do your substitution. Oh, negative 2, sorry. That actually, if I had just left it as positive 2, you could not solve that because you do not know what the function is at negative 2, or at positive 2. So that would just be one of those where you would say there's no solution because you don't have enough given information. So f of negative 2 is 5 minus g of negative 2, which is negative 3, which becomes 5 plus 3, which has a function value of 8. And then if we do f of g, oh, that parentheses turned out ugly. That's a lot better. Of negative 2, not positive 2, is equal to f of negative 2 divided by g of negative 2, which is equal to 5 divided by negative 3, or more simply put, negative 5/3. So pretty simple, pretty straightforward there. If you know the function value, you can just go in, apply it, and it's pretty easy to deal with. So now what if I said, let's combine two functions? So first we're going to do f plus g of x, where f is 4x squared minus 1, and g of x is square root of x. So the first one's pretty straightforward. So if I do f plus g of x, that's just f of x plus g of x, which is equal to 4x squared minus 1 plus the square root of x. And if you want to just throw them in parentheses just to keep up with that, go for it. You can never, well, I won't say you can never use too many parentheses, but it never hurts to include them. And the reason that I include them is if, let's say, these were swapped and it was minus, that minus needs to distribute to both pieces. So you don't want to accidentally not misdistribute, but not distribute correctly your negative. It's got to apply to everything of the function, not just the first term. But with this one, we can see there's not really anything we can combine. If we'd had like 3x plus 5x, we could make that 8x. But here, everything's just kind of is what it is. Nothing really much to go off of. And in terms of, is there a particular order? If you really want to be pedantic about it, you don't have to. This might be the quote unquote the best way to write it. And typically you would say the best way because it's descending from powers of x. Because remember, square root of x, like we talked about previously, is equal to x to the 1/2. Which we're actually going to have to use that for the next part. So if I'm going to do f of x times g of x, then let's see, f of x is 4x squared minus 1. But I don't want to leave it as x to the 1, or I don't want to pull in square root of x because I'm going to have to combine, or I'm going to have to multiply the same base, which means you have to add the exponents. And square root of x times x squared looks weird. So let's rewrite it as a power of x. And when you do that, 4 times x squared, or 4x squared times x to the 1/2 becomes 4 times x to the 2 plus 1/2, because these have the same base, which is x, which means you just get to add the exponents. And then minus, well, just minus x to the 1/2. So this would be 4x, and this would become 4 over 2 plus 1/2 minus x to the 1/2, which is going to equal 4x to the 5/2 minus x to the 1/2. And that's the better way to leave that. The reason I say that is 4 times the square root, which I could leave that off, of x to the 5th minus the square root of x, that's a little bit messier versus just leaving it as x to the 5/2 minus x to the 1/2. Just makes your life a little bit easier. Now, this one is kind of almost doing the abstraction part again. Here are the graphs of f and g. You probably could figure out what the original functions are, but don't think about that right now. Just look at the picture. So we're going to determine the domain of f plus g and g, f over g, and then we're going to find what is f plus g of 1 and f over g of 1. So I would say for f and g, it doesn't look like there's any values that are excluded. So I would say the domain of f and g are both negative infinity to positive infinity, because I don't see any values that you can't plug into either one. Now we need to do the first one, f plus g, and, or sorry, let me finish this. Domain of f and g are both negative infinity to infinity, which means if I do f plus g, it also has a domain of negative infinity to infinity. But look at f divided by g. Where does g equal to 0? Well, if we look our two problem points are going to arise here and here. This is the point 2, 0, and the point negative 2, 0. So the domain for f over g is going to be negative infinity to negative 2, union negative 2 to positive 2, and then union 2 to infinity. Because when I do f over g, I have to exclude any places where the denominator is equal to 0. And so the only two places where g is equal to 0 is when x is equal to positive and negative 2. So those points have to be excluded. All right, so now that we've got that out of the way, now let's get to the actual evaluation. So let's see, at 1 on g, I'm at 3. And then on this one, when I'm at 1, I'm at 2. Or sorry, when I'm at 1, I'm at 1. So now if I do f plus g, that means I want to do f of 1 plus g of 1. So f of 1 is 1 plus g of 1, which is 3. So f of 1 plus g of 1 is equal to 4. Now, that would mean that if you plotted that, because this is f of g, or f plus g of 1, that point would be plotted here on the graph. And notice that I just get those points by adding the two functions together. Now when we do f divided by g, so I have f of 1 divided by g of 1, which is going to be 1 over 3. And now I'm not going to try and plot 1 over 3 because this graph has already gotten really cramped as is. So that's how you identify the domain of a combination of functions. And it's also how you put these things together. And it's also how do you do the combination of these functions. And this one's the specific case where you don't actually have what the function's algebraic or you don't have the algebraic representation of the function, you just have the graphical representation. So this is just kind of a nice way to go about it without having to, I won't say think too hard about it, but without dragging in the actual algebra of it. Now, this is the more go-to idea when we say composing functions. When I say function composition, typically the main idea that comes to mind is f of g of x, or g of f of x. Now, I typically tend to avoid the notation with the little circle here. If I say f of g of x, I tend to just write it this way. But you want to be familiar with both versions because some people have other preferences, and it's kind of just being able to read it in a different way. You don't want just the way it looks to be the confusing part. And it is important that the order of composition matters. There are very special functions where the order doesn't matter, but those are, I won't say few and far between, but most functions that you're going to encounter, the order does matter that they're composed in. So just be aware. So this is an example of how to be aware of those. So f of g of x. So what this is this is saying take the function f and evaluate it at the function g of x. So the function f is x squared. So what this means is if you did f of 2, you would plug in 2 for x and you would get 2 squared. If it was f of 5, you would plug in 5 for x and you would have 5 squared. So what this means is I've got g of x and I'm going to square all of it, which is going to give me x minus 3 squared. Now, if you want to expand it out, go for it, but I recommend just leaving it like this, and you'll see why in a second. Now, if we do the opposite way, g of f of x. This means I need to take f of x and plug it in wherever there's an x in g of x, which that's going to give me f of x minus 3, which is just simply x squared minus 3. Now, the reason I said not to expand this out, which if you expand it, it's x squared minus 6x plus 9. If I want to figure out what f of g of 6 is, I would rather plug 6 into here, because then I only have to do 6 minus 3 and square it, versus square 6 minus 6 times 6 and then add 9. So f of g of 6 is just 6 minus 3, square that, which is going to be equal to 3 squared, which is 9. So you would get the same answer, but you just go about it in a different way. Now, one other thing you can do is, this is kind of going back towards kind of the way that we did with the graphical representation. If you do f of g of 6, first you could calculate what is g of 6. Well, g of 6 is equal to 6 minus 3, which then gives you f of 3, which would then give you 3 squared, which is 9. So that's another way to go about it. You can do the composition on the inside. You can just evaluate it at g of 6, and then, or you can evaluate g of 6 and then plug that value in for the function f. Sometimes that might be the better option if you're not required to do the composition, because if you're not going to do the composition and then do it multiple times, sometimes it might just be easier to sorry about that. If you only have to do one calculation, it might be faster just to do this second way, because if you have to do multiple compositions, it's probably easier just to find f of g of x or g of f, or whichever order it is, versus if you only have to do one computation, you save time, because then you don't have to go through this process of finding what is f of g of x. you can just go, okay, g of 6, that's 3. And so then f of 3 is 9. So then similarly, if I do g of f of 6, that's just going to be 6 squared minus 3, which is 36 minus 3, which is just 33. And you could do that one similarly to the second way. Now, just a word of caution. Like with the division by 0, you have to be careful when you compose g of x or f of g of x. Because if g of x is not in the domain, then you can't evaluate it at f of x. So like if you had, one example would be, so let f of x be equal to the square root of x, and let g of x be equal to, let's say, 3x minus 4. Then if I say, what's f of g of 1, you'll run into an issue because, so put these two together, f of g of x is equal to the square root of 3x minus 4. G of 1 is going to be equal to negative 1. So this would be, what's f of negative 1? But negative 1's not in the domain. So f of negative 1 does not exist. So you have to be aware of what's in the domain of G. And it's when you evaluate, what's the best way to put it? It's when you evaluate it, because when you evaluate g of x, is that result still in the domain of f of x? Because in this one, you think at first f of g of 1. Okay, 1's in both of the domains, no big deal. But as soon as you evaluate you evaluate g of 1, that's where you run into the issue. Because g of 1 produces a number that's not in f of x's domain. So just be aware of that and be careful. And with that, we'll move on to inverses next time, and that should wrap up chapter 3.